Yeah, good morning, everyone. Great pleasure to be here back in beautiful Santa Barbara. So I'm going to give a kind of an overview of some work that some of it goes back quite some years, but is also relevant to current things we're thinking about. And the talk brings together a few different things. One is search for spin liquid states that may be found in systems with strong bond-dependent interactions, right? What we refer to as KITP interactions. I'm also going to talk a little bit about work that we've done on one-dimensional spin chains, Ising chains, this famous material cobalt niobate that we've already heard and seen a few slides from earlier in the talk. And then, if you will, the amalgam of both of these things and what insight from the work that we've done on 1D chains may tell us about the search for quantum spin liquids and bond-dependent interactions in higher dimensional systems. So before I do that, let me thank the people who make this work possible. So my former postdoc, Chris Morris, who's moved on from science now, but was involved with some of this work even recently. My former excellent student, Xinshu Zhang, who's now a postdoc at UCLA and led the work on the honeycomb magnets that I'll tell you about. Various collaborators from Hopkins, Tyrell McQueen, Syed Kupaya, Natalia Dritchko, who's here, Oleg Chernyshov, longtime collaborator, did I mention Tyrell McQueen, longtime collaborator Bob Kava from Princeton, his former postdoc Rudin Zong, Colin Broholm, also from Johns Hopkins, Colin's student Tom Halloran, a collaboration with Thomas Room and his group from Estonia. And I want to, in particular, point out a collaboration with Ribu Kall that, well, actually, I should have updated this. Ribu was at Kentucky when we started collaborating, but now has moved on to Penn State, and his former student, Nishita Desai, and is really an insight, in particular, with from the work and discussions with Ribu, which basically pushed this topic forward. So just very briefly, I always give my conclusions in the beginning, so when I invariably run out of time, you've seen them. I'm going to tell us, in general, the story about bond-dependent interactions in cobalt-based magnets, and tell you a little bit about the work that we've done on cobalt niobate, the best material realization of Ising's model, some review of some old results, but still beautiful, and then some recent insight both into the physics of Ising chains and duality relations, but also into bond-dependent interactions. This has a number of interesting features. We refer to the model that we describe it as a twisted KITP chain. It has an interesting mapping to Su-Schrieffer-Heeger model, which was famous in the context of polyacetylene. It is the first and maybe simplest version of a topological insulator in one dimension in that case. And then if I have time, which I probably won't, I'm just going to barely touch on the work that we've done in barium cobalt arsenic, which we originally wanted to think of this as a two-dimensional version of the Ising bond-dependent interactions that we find in the KITP in the 1D compound, and it's most likely not, but perhaps some way forward can be seen there for possibly realizing systems that do have strong bond-dependent interactions. Okay, so I'm just going to say this very briefly because I think this is review to everybody here in the room. The main focus in this field of KITP quantum spin liquids has been on D5 pseudo-spin 1/2 ions, which in the context of things like ruthenites and iridates. And although this has been a very, very interesting field, and there may be spin liquid physics that is inside these materials, in particular things like the ruthenites, these materials all have some substantial non-idealities, which other, let's say, other terms that are not KITP that can stabilize other ordered states and move one further from tractable models that you can make immediate theoretical connection with. And so there's some impetus to discovering a material which has, let's say, smaller non-KITP terms. And in this regard, there was recent predictions that cobalt compounds, 3d7 ions with the kind of high spin cobalt +2 state, may realize, which do have a pseudo spin 1/2, but may also realize this strong bond-dependent interactions, and in particular, those of this KITP variety. I'm not going to talk about the details of this. Maybe I'll get back to it a little bit later on. But these, among other aspects, these non-idealities and things like alpha ruthenium chloride, that if we can induce some kind of spin liquid state in those systems, this is typically has been done by destabilizing that order by applying a large magnetic field. And it looks like in many of these cobalt compounds that you can destabilize some order, much smaller fields. And so that's led, this kind of phenomenological perspective has led to some idea that those compounds may be a good kind of starting point for looking for this kind of systems. Okay, I'm going to get back to this, honeycomb lattices and bond-dependent directional easing interactions, but I'm going to get there in kind of a roundabout way, and a diversion that may seem only peripherally related topic, and that's that of the Ising chain. So Ising chain in transverse magnetic field is perhaps the simplest model we have of a quantum phase transition, right? So we think about spins on a chain, they can be ferromagnetic, and we'll take this system and apply a large transverse field to it. The system, let's say zero field, is twofold degenerate, all the spins can be up or all the spins can be down. We apply a large field to it, and we could imagine in the large field limit we spin polarize. So you go from a twofold degenerate ground state to a singly degenerate ground state, and this doesn't, of course, happen smoothly, so there has to be some kind of phase transition, quantum phase transitions. So quantum phase transitions in general are characterized by a collapse of energy scales near the transition, and many quantum phase transitions also are characterized by duality relations. If I know something about the system on one side of the transition, I can learn something about the properties of the system on the other side of the transition. So we're going to come back to this as well. If you look in let's say intuition and the theory of quantum phase transitions, which of course has had a huge impact in the field of condensed matter physics, was really kind of first understood and worked out in the context of simple spin models, and in particular in the case of the Ising chain in transverse magnetic field. And so it's a kind of a model system for understanding quantum phase transitions. We have, I'm sorry, maybe I'll talk about that part of it later. Here. So we've heard about, we've seen this kind of plot earlier, and this comes from this famous paper of 2010 of Radu, where it pointed out this material here, cobalt niobate, which belongs to a class of minerals that are called columbite, may be the best material realization we have of Ising's model. The material itself is this kind of zigzag chain of cobalt ions surrounded by these distorted octahedra in this fashion. And when you take this material and you cool it down, it has a principal, largely ferromagnetic interaction along the chains. The zigzag is going to be important. We'll talk about it in a moment. But a weak anti-ferro interaction between the chains. And you go, as you cool this thing down, and you form these very, very long-range one-dimensional correlations that are along the chain. Old neutron scattering that kind of predates this era showed that the correlation length, it's something around about 3 Kelvin with something about 100 lattice constants along the chain. And then you go cool down to lower temperatures, and there's two phase transitions where ultimately this is through incommensurate transitions where ultimately it orders in these 1D ferro chains, which are then anti-ferro coupled to the neighbors. And this is a old plot of the heat capacity versus temperature. And you can see this is the plot of the non-magnetic analog zinc niobate here, which kind of just comes down smoothly in the fashion that you would expect for an insulator with phonons. But then there's a deviation around 20 Kelvin here of the heat capacity. And that's where you start to build up these very long one-dimensional correlations before blunk, blunk, you come into this low temperature state and through these two transitions where you essentially have anti-ferro physics between the chains and ferro along the chains. So I'll show a little bit of some of the data that I'll show you now was the essential idea was in Radu's paper, but I think our data is rather pretty, so I'll tell you about that. The physics of this, I'm sorry, I'm having a hard time working this. Oh, go back. Okay, yeah. So the way we think of excitations on this on the chain in this ordered state is as we think of the elementary excitations of these domain walls. I'm going to come back to this with a linearly confining interaction, which essentially comes from the result of this anti-ferro interaction between the chains. If the system was purely Ising, it would be kind of simple and boring, but of course there's other terms in the system which are not just pure Ising, which, if you will, allow zero-point motion to these domain walls, and that's essentially kinetic energy. And one can solve this in a kind of a simple Schrodinger equation, which I'll come to in a moment. The principal experiments that we're doing are time domain terahertz spectroscopy. So these are experiments that we can do in a laboratory on an optical table. We use the time-varying electric fields of the system that they basically to measure these pulses, but our time-varying electric field has a time-varying magnetic field, and it's the time-varying magnetic field which couples to spin in the system. So it's essentially a way of doing high frequency, when we put it in field, high field electron spin resonance style measurements. Unlike conventional electron spin resonance, we work not just a single frequency, but a whole range of frequencies, so we don't have to sweep the field working at just a single frequency, but we can actually, let's say, go to a field and get real spectra and get spectroscopic information. Okay. I'm going to talk about the details of this. If you're interested in the experiment, of course, I'm happy to talk about it. So there's data. So we take the system, we cool it down, and when you, this is a plot of the absorption versus frequency in the terahertz range, which corresponds to a few milli-electron volts. When we cool it down from about 40 Kelvin or so, remember I said around 20 Kelvin is where you start developing one-dimensional correlations along the chain, and that's where you start to see this kind of structure here. The structure gets larger and more prominent, and you go from the incommensurate state to the commensurate ordered state, and that's just going from there to there. Just boom, all of this sharp spectra comes out. So we can concentrate, let's say, just on the lowest temperature spectra. And this is, again, a plot of the absorption, which is proportional to the susceptibility as a function of frequency. And you see this, just remarkably rich spectrum M1, M2, M3, using Radu's notation all the way up to M9. Another peak here that we originally called 2M1, and then this broad blob here that we originally had associated with a continuum of states that are associated with these M1, M2, M3 are associated with bound states, basically, of domain walls, and we had associated this blob here as a continuum of M1 states. But now, as I'll show you, we have a kind of refined understanding of this. So this is again from our old work on this. That's energy versus an index, M1, M2, M3, M4, M5. And this can be solved in terms of this Airy function model that we heard about in talks already in this conference here. You have a kinetic energy term, a linearly confining potential. If it wasn't x here, but it was x squared, you would solve this in terms of your old friends, Hermite polynomials, but since it's x, you solve it in terms of your new friends, this class of Airy functions. The energy eigenvalue structure has this particular form here with these z sub j's, where the z sub j's correspond to the negative roots of the Airy functions. Now, one of the things we can do with this is, like atomic physicists, we have very rich spectra, and so we can fit that rich spectra and then learn about the wave functions. There was a question, I think, in Monday's talk about these, as has been referred to sometimes, these Zeeman ladders. How do you couple to them? Right? You know, one of these high-order states, M5, M6, has a lot of spins in it, and terahertz, because of magnetic dipole coupling, and just like with neutrons, you flip essentially a single spin. But you can reveal this in the wave functions, and so the way you should think about these excited states is really superpositions of different numbers of spin flips. These are not spin eigenstates. Let's say the transverse field mixes different spin sectors of different spin flips, and these are the wave functions right here. This is M1 we can think of as just as a superposition of a little bit of one spin flip, a little bit more of two spin flips, a little bit less of three, a little bit even less of four, et cetera, et cetera. M2, has this particular pattern, and this kind of oscillating pattern that you can just kind of barely make out. That's actually the Airy functions there. So again, we're kind of like atomic physicists, right? We have very rich spectra, and we can fit it and then and learn enough really to know something about the wave functions. Okay, so now that was our work from some years ago, but our real interest here was in the quantum phase transition itself, and that was my original focus on it. So quantum phase transitions, as I mentioned, are characterized by a collapse of energy scales. When you take the transverse field and apply it to the Ising chain, essentially You can think of it as tuning the bandwidth of the system. So we can, this is the Hamiltonian here of the simple transverse field case. The elementary excitations of the system are these domain walls. The energy dispersion of them in the simple nearest neighbor Hamiltonian comes out in this particular fashion here, where the energy gap to make a single domain wall goes like 2J times 1 minus G, where G is the transverse magnetic field. And it's important to note that one of the things that happens as you tune from the ferro side to the para side in this transition is that the character of the excitations change dramatically. So you go from having the elementary excitations or domain walls on the ferro side, but then there's simple spin flips on the high field, or sometimes referred to as the quantum disordered side. There's an essential difference between these guys in that you can, this is a very non-local object, you can only make 2 at a time of these, right? So you flip a single spin and that corresponds to 2 domain walls. And so it's interesting to note that put in this particular form here, let's say given some distance G, or 1 minus G from the transition, the gap to the elementary excitation is the same magnitude on both sides of the transition. But you gotta make always 2 at a time here. And so as I said, the quantum phase transitions are characterized by this collapse of energy scales in their phase transitions. But what you expect in the Ising case, in the transverse field Ising case, is this gap which closes twice as fast on the ferro side as it does on the para side. Okay? The other thing that you would expect is that you, on the ferro side, have kind of a broad continuum excitations because there's many K minus K pairs you could make of these domain walls, whereas you get a sharp peak on the paramagnetic side. This factor of 2 and between this gap and that gap, and the fact that there is this correspondence between the excitation spectra on the 2 sides is a characteristic for the Ising model of so-called Kramers-Vonnier duality. So quantum phase transitions in general actually are characterized by duality relations, as I mentioned, and so this is how this manifests here. Okay. So let's look at the spectrum. So this is a plot again of the absorption as a function of frequency, plotted in a slightly different fashion. These experiments were done in Thomas Room's group in Estonia. They could go out to very, very large magnetic fields, larger than we could do in my lab, so we did the experiments there. The transverse field, the zero transverse field case is down here as this spectra, and I apologize that it's all kind of squished in, but you can see what happens. You apply the transverse field, and at first there's this kind of, we'll come back to this in a moment, there's this kind of squishing of the spectra, if you will. This kind of goes up a little bit, and this kind of comes down. But then what happens is this kind of peak splits off and comes back up on going from the ferro side to the para side. And what we plotted here is the kind of threshold of the low energy peak and the threshold here from the ferro side to the para side. And those 2 dashed lines differ by slope factor of 2. So that's the universal factor of 2 that's associated with the Ising universality class that essentially parameterizes this Kramers-Vonnier duality, or perhaps putting it a little bit differently, the conservation of domain wall parity in the ground and the excited states of the system. So universal factor of 2 that comes out in this material. So that's one thing that I think is of interest and importance, and I think really the first experimental demonstration of Kramers-Vonnier duality in a system like this. Now, the other thing that came from this, and this data we actually had for a very long time, and this is where Ribu Call enters the story. There were some things we were puzzled about in the data for a very, very long time. And one of the things that we were puzzled about was this thing that I mentioned earlier, this kind of narrowing, if you will, of the bandwidth. You can see how the spectral feature kind of comes up here, and this one kind of comes down, if you will, before then eventually coming up. Another source of confusion, at least to me, was the source of the quantum motion at 0 applied field. So if I have, in the normal transverse field Ising model, if I have no transverse field, it's just a completely classical model. If I flip a spin, the spins just kind of sit there, right? There's no source of quantum mechanical motion at all. So at 0 transverse field, this is actually pretty well modeled by the transverse field Ising model with just some transverse field which has been thrown in, and there was some there's been very nice numerical work over the years that was in that work. Typically they would just put in a phenomenological transverse field without a whole lot of thought about where it might come from. It was coming from somewhere. So this was a bit of a mystery as well. Now, you can see this maybe perhaps better here in this case. So this is a plot of, back to data taken in my lab, of this susceptibility plotted out of the page, colored here. So this is in the state where you have no long-range order, but just very long 1D correlations, so at 3 Kelvin. And then this is at low temperatures, so you can see just, again, all of this kind of beautiful, rich structure. The data that I showed you previously, which is also shown here, is just like a cut along the zero field direction, and then you can see the field evolution of all of this as you apply the transverse field. And again, remember the quantum phase transitions are characterized by the collapse of energy scales. You expect things to go down towards the transition, and they don't. They do that eventually, but initially they're actually coming up. And so this was a mystery. I had some thoughts about that. I wanted to mention one more thing. We initially also thought in our original paper on this that this region up here was essentially a continuum built out of 4 domain walls at a time. So it was like it was bound states, but it was a continuum of bound states. But this frankly never made sense when you took the context of this data, because you would expect all the energy scales to come down. But in fact, you can see these guys are actually going up here in energy. So that picture, didn't hold up when we started thinking about the transverse field case. So there was some confusion about this. Now, one of the things that we had thought about for a while was that the zigzag chain is perhaps relevant. The thought that I had had for a long time, but couldn't quite put together, was that the zigzag consequence of the zigzag chain was coming from the fact that there was kind of an internal transverse field, which was even and odd, plus and minus on the different, that was corresponding to the different bonds. This could give you the source of transverse field from the beginning, even at zero field. Perhaps this was a field that was allowed by symmetry. Maybe you got it when the system ordered because you have some kind of anisotropic G-tensor or off-diagonal G-tensor. But that didn't quite make sense either, because the situation was that these dispersions were found even in the disordered case. Right? So it had to be something that was there, really kind of intrinsic to the crystal structure. This zigzag, if some of the effective transverse fields that these ions saw were positive and some were negative, then it did start to explain the data, because we would apply, let's say, a positive transverse field from the outside world. The positive bonds would get bigger, the negative bonds would go back towards zero, and you could imagine then the bandwidth would shrink. This is where the conversations with Ribu entered, and it was actually the very last talk that I went and gave right before the pandemic. I was giving a colloquium visiting University of Kentucky. He was the last person on my schedule that day, and I used to end this talk by talking about what we didn't understand. So we went back to his office, and really within like a half hour had worked out most of it. And the essential point is making a connection to this notion of Kittai physics. Right? So that's our zigzag chain there, this picture from Radu's paper, and there's the hexagonal portion of the hexagonal lattice that people have used to model this Kittai of bond-dependent interaction in systems like rutheniates and iridates. And here the idea is that there is an interaction, let's say, in the x direction along the green spins that has its is Ising-like, but is essentially oriented along this bridging from the octahedra here, this kind of rectangular shape here that you can see kind of on its side. And then there's another one in this direction here, and then another one there as well. And the connection then kind of can become perhaps originally immediately clear. We're going to get rid of that other octahedra and slide these guys over. And one can then perhaps, if you have a notion, as I discussed, that cobalt systems have this proposal for strong bond-dependent interactions, and you can think of cobalt niobate as a 1D zigzag chain of the Kitaev model. It immediately gives you some kind of route forward for understanding how you could get this physics. So inspired by these notions here, what we did in the analysis is we assumed that the cobalt nearest neighbor interactions were of this Ising form, but kind of due to the complex local chemistry that's involved, these octahedra are not just trigonally distorted, but they're squashed from the side. It was going to be complicated to do a real analysis. We decided just basically to constrain all the parameters by symmetry and then set them by experimental input. And so it gives kind of a very intuitive model which captures essentially our data very, very well. The idea is that we're going to have spins on this chain, 1D chain, where the Hamiltonian is set in this particular fashion here, where you have this Ising interaction N1 between two spins, and then N2 on the next case. And so in local axes, you think of it as the easing interaction just kind of goes down the chain and flip-flops, plus, minus, plus, minus, plus, minus as you go down the chain. In the strict Kitaev case, the octahedra would give you that this angle is 40.3 degrees. We don't expect that that's going to be the case here. So again, we set this angle as the kind of easy axis just as a free parameter and fit it to experimental data. This idea gives you a number of kind of important insight quite quickly. This is done in the framework and the coordinates of these local axes, but we can put it in the global XY coordinates. And then you see what happens is you introduce this particular term here, which has XY, which is the X spin interacting with the X component interacting with the Z component, which changes sign from bond to bond in that fashion. And we can get more insight if you say work in the limit of very small twists. So we ultimately fit the spectrum to an effective twist of this local axis of 17 degrees, but let's work in the limit of very, very small twists just to get insight. It's almost the normal Ising model in transverse field then, and you can see this -1 to the n factor propping up, and this thing in the prefactor here, that's the transverse field times this term here, which is alternating sign from site to site. And so now we have a lot of insight to what's happening here. We apply, let's say, a positive, the system has at 0 external field bonds which are positive and minus, transverse fields that are positive and negative of some particular magnitude, which is set by the Ising exchange. We apply a transverse field. Some of the bonds get larger magnitudes, some of them get smaller magnitude. If this was the only physics that was going on, there would be some extraordinary field where you would tune, let's say, the odd sites to have 0 transverse field, or the odd bonds to experience 0 transverse field, and the system would break up into localized dimers. And that is our data on the top here. This is in the case where we don't have the long-range interaction. We can think of it as the ordered, the non-ordered state where it's just the long-range spin correlations going along one chain, and then when the system orders at low temperature with all this remarkable structure. And this is the DMRG calculations from Nishita and Ribu, who were able to basically fit the data in an excellent fashion with just these 2 free parameters, input parameters, the Ising exchange interaction and this angle that we just allow to be free, which in this case is 17 degrees. Very often in physics, you're kind of on the right track when you come up with some idea that explains a bunch of things, and then you end up being able to explain things that you didn't even realize needed to be explained. And one of them is the following. So if you apply, if the system at 0 transverse field has these 2 Ising domain wall bands, you apply the transverse field to it, and the effect of that is to open up a gap in these guys. So we come in with a photon, we flip a spin, we make these 2 domain walls, and there are 3 possible ways to make the domain walls. We can make 2 domain walls in the bottom band, and that gives us this particular feature here, and we find correspondence of that in our spectra. We can make a domain wall in the bottom band and one in the top band, and that is this feature right here, or we can make 2 in the top band in this fashion. Okay. So these are all the ideas worked out in our paper in 2021. You can tune the bond-dependent interactions in field. This gap that shortly before our picture, which is this kind of model, the Kitaev interaction, there was a paper by Radu and Sid Parameswaran were pointing out that this kind of even-odd interaction is allowed by symmetry. We should have kept going with it and thinking about more aspects of the spectrum. There's this recent paper also by Radu and Leon. I think we heard about some of this work the other day. This is our DMRG calculations, and one of the significant things about this particular paper is discuss the presence of bound states in the spectrum. And so this is our DMRG calculations published a few years ago, but completely uncommented on. And it corresponds with the bound states that we heard about in Monday's talk on this here, and this corresponds to the bound states. These kind of sharp features in our spectrum as well were also something that were puzzling us, but we didn't get into the details, but it's discussed nicely in this paper. Okay, so I have a few more minutes, I think, right? 1 minute left. Okay, I'll need about 2. And so I wanted, so what do we have out of that? We have this notion of a 1D chain with bond-dependent interactions, which have a strong similarity to that of proposed for cobalt 3D7. So when we were working on that, at the same time, we started to think about the physics of this particular material here, barium, cobalt, arsenic. And I have to say, I was pretty prejudiced to the fact that cobalt 3D7, having worked on, found these bond-dependent interactions in the context of the 1D chain, that now the 2D case was going to be a rather straightforward application therein. We have for many years been fortunate to work with Bob Kava, who has supplied and working in the context of our Center Institute for Quantum Matter at Johns Hopkins, has been involved with it for a long time and working on lots of interesting quantum spin systems. And Bob and his former postdoc, Rudong Zhang, had published this interesting paper on barium cobalt arsenic. Barium cobalt arsenic is a hexagonal magnet made of cobalt edge-sharing octahedra, laid out in the 2D plane as such, and it was pointed out by Rudong that when you cool this thing down, there's various kinds of magnetic ordered states, but very, very, very small magnetic fields. You can basically suppress that and go into some particular region here of this. The provenance of it was kind of unclear, but they interpreted it as being consistent with the Kitaev quantum spin liquid case. This fact that this, they made an analogy with the phase diagram in alpha ruthenium chloride, where a transition of a similar variety happens something more around, let's say, 7 to 8 Tesla, something like that. But you can see here it's happening closer to about half a Tesla. And the inference was that this material may be a material that has dominant Kitaev-like interactions in this regard. We had also done some experiments on this, and for instance, one of the things that we could see was that when we do our terahertz experiment, this is terahertz susceptibility as a function of frequency. When you cool the system down at small magnetic fields, there's a very large and very prominent peak that's associated with some kind of magnon-esque feature, probably associated with antiferromagnetism. But when we apply a magnetic field to it, this is an out-of-plane field around 3 Tesla. This thing just gets completely washed out altogether, and you get this kind of very characteristic broad continuum behavior here that had systematics that didn't seem to be consistent with that of magnon decay. This happens in this case at 3 Tesla, or 3.5 Tesla. Again, the point from this is perhaps that these non-Kitaev terms are much smaller in this system. Here's some of the actual data in this regard. This is plotted out of the page as susceptibility as a function of magnetic field, and you can see this very sharp magnon peak just goes away, and you get over into this broad kind of continuum behavior as such. If to get something similar in terms of suppressing the magnetic order without a plane field in alpha ruthenium chloride, I think you have to go to something like 80 Tesla. This recent experiments have just been done. So our original thinking was that this, in fact, was going to be a very good example of a Kitaev system. My colleague, Colin Broholm, did a very systematic neutron scattering work, and what it apparently looks like is that in the end, the bond-dependent interactions are quenched in the system. It is very well described by an XXZ model, and this has been consistent with some kind of theory work from people like Arun Parmakenti and Stephen Winter and others. So this is the paper. I should have the actual reference up here. This is in PNAS now by my colleague Colin Broholm and his student Tom Halloran, and they show basically that the comprehensive data set that is via the neutron scattering and also looking at magnetization can be modeled by XXZ plus a J3 term, and this seems to account for most of the physics. So the question is, in the end, and I'm finishing right now, what's gone wrong in barium cobalt arsenic and what's gone right in cobalt niobate? It's not quite entirely clear in this regard. It's been emphasized that materials like barium cobalt arsenic perhaps have too large of a trigonal distortion. And I actually don't think that's probably true. If you look to see the degree of crystal field splittings that come in barium cobalt arsenic, they're about right here somewhere and quite consistent with in the calculation with a regime where Kitaev interaction should be large. Cobalt niobate is not just a trigonal distortion, it's actually squashed from the size as well, but if we just kind of get a rough feeling of energy scales from the anisotropy of G factors, cobalt niobate is something about right there, also in a regime where the Kitaev interaction is quite large. And so I suspect it has to do with some possibly harder to model chemistry, that the fact that the direct exchange is probably too large in things like barium, cobalt, arsenic, and is suppressed in materials like cobalt niobate. But I'm hoping that this is going to be a topic of interest. And I'm hoping also that cobalt niobate, with as a system, which is, as far as I know, that is really shows the most incontrovertible evidence for bond-dependent interactions, may be kind of a source of inspiration for us designing two-dimensional frameworks that may be a platform for quantum spin liquids. So I'm out of time. You've already seen my conclusions, and I'll stop there. Thanks very much.
Peter, for the cobalt niobate, the one-dimensional zigzag chain has lower symmetry than the ideal honeycomb. The minimal model for the nearest neighbor exchange matrix in the honeycomb case contains 4 parameters. In the case of zigzag chain, it contains 6 parameters. As Radu has shown that one can successfully remove 2 of them. Yet your model contains fewer parameters, and part of my question is that is there any, what was the hope that you can describe it with just 1 or 2 parameters? And the second thing is that I think Radu's latest papers contain all the parameters fitted to some high degree accuracy. Can one map them to your rotated, you use different reference frame, can you rotate it there and actually tell us what is the value of K, gamma, gamma prime, and some other terms?
We haven't done that analysis yet. We should. So Radu could probably comment more expertly, but my recollection is that, so we have this simple model, right, and its virtue is its simplicity of the twisted. When you go to the global coordinates, then you generate effective SX, SY interactions. I'm just kind of restating your question. And the question is, can you understand our twisted model in the context of, let's say, the size of the parameters they get from parameterizing things in terms of X, Y, Z? And I think the answer is generally no. So the model does a very good job at let me just finish, at explaining Q equals 0. But it doesn't do as well for getting things like the kind of the large bandwidth, particularly in large magnetic field put on the A direction. And in particular, the thing that our model doesn't do is give you large enough XY term. So the SX and SY interactions put in the global coordinate frame, I just think can't be large enough. If you make it large enough, then you've made a bandwidth which is way too large, right? So we can tune SX, XY, to say the symmetric XY exchange by just twisting this thing more. But when we do that, then we generate a much larger bandwidth than is observed. So,
right. I understand the value of the intuition you provide in the simple model, but what I question is the actual statement about the dominance of the Kitaev term.
Well, I think that we should do the exercise, and we haven't done it. But I think that you can go in. What we should do is take what we've done, put it in the context of JK, gamma, gamma prime, if you will, and go from there, and we should know. Yeah.
Peter, thanks for a very nice talk. So I have a brief comment and then a question. So the comment is that my recollection of Radu's work was to point out that if you just took an Ising model in transverse field, you wouldn't see any bound excitations. You would see a two-king continuum. In fact, what was important to realize is that the chains have, albeit weak, but the Ising coupling, which effectively acted as a longitudinal magnetic field. Yeah. And that's what allowed the mapping on the logic of E8 model. So somehow none of that appeared in your talk. That's my question. And I know, somehow it wasn't emphasized.
First of all, that's an idea that goes back to work, I think, in the 70s or 80s for the Zeeman, basically a Weiss mean field that comes in from the effect of the neighboring.
Right, but chains. Was it in your Erie function model or the different
that's implicit. That's what I said. You get this ferromagnetic chain, and that's these unconfined domain walls, if you will. But in the low temperature state, then you have ferro chains, which are anti-ferro coupled to their neighbors, and they order. So it's an anti-ferro, in the transverse direction. And that anti-ferro ordering is what provides the Weiss the Weiss mean field.
Okay, so then I missed that. Okay.
Confinement. So I showed, like, from the experimental data, generally two sets of data. I can go back a little bit to make it clear. There, for instance, right? So the data at the top is our experimental data. On the left is just above the ordering transition. On the right is below the ordering transition. And you can see how the structure develops when you get this confinement. Right? So on the left is unconfined domain walls, and on the right is confined.
Gotcha. Okay. And then, thanks. And then the question I wanted to ask, so how does your parametrization, right, which introduces the Kitaev-like dependence, bond orbital dependence, how does it differ from this recent work where Radu is involved with Sid Parameshwaran? Well, what they insist is on the presence of this glide symmetry. And I don't remember their paper in detail, but it seems...
These are consistent with that. I mean, the symmetries are in the model that we wrote down as well. We were just kind of coming at it from a different perspective, not motivating it via terms of symmetry, but kind of looking more at the microscopics of where it might come from.
Okay. And perhaps last question, what aspect of the original data back in 2010 was not explained by the E8 model that prompted you to introduce these extra terms, bond-dependent ones?
The fact that there's a bandwidth at zero external transverse field. So the first data that I showed, or if you will, let me go back a little bit. There. There. So the data at the top is with zero applied external field, right? So you see at 3K, there's this broad continuum behavior. If it was purely Ising model, that's just spin flips with no dynamics at all, right? So you would just get some peaks at whatever energy they happen to be at. There would be no width. So there was what it looked like, and there was no accounting for this, is that there was some internal transverse field, but coming from what, nobody knew. There was lots of numerics that had been done, and they just put in a phenomenological transverse field without a notion of where it was coming from. But, and that did a good job. So the question is why, and where might it be from? And then it looks like it's from this term, which has this kind of even-odd character on the different bonds.
Really nice talk. Yeah, so I have two questions. The first one may be very similar to Sasha's question, but I'll rephrase. So for the cobalt and niobate, the twisted Kitaev model, the zigzag chain, in the twisted frame, ideal octahedra, still there's two bond-dependent Ising couplings. You can have the Kitaev coupling, which is orthogonal to the plane, and just an Ising coupling along the bond vector connecting two spins. It's not even clear to me, like, maybe you included both of them, but then did some rotation around the Ising axis, or did you just include one of them? And I wonder if that makes a difference.
Get it. What two?
Yeah, so there's the Kitaev coupling, which gives you three orthogonal axes for the honeycomb, or two orthogonal axes for the zigzag chain, and then also a bond-dependent Ising coupling, where that Ising coupling is just along the bond axis. So it's not two orthogonal direction, and both of them are in the plane.
Right.
So these are two different bond-dependent couplings that I think you can include both, and maybe they rotate to a single parameter since they're Ising spins, but that's what I was wondering about.
Yeah, let's talk about it. Yeah.
Okay, sounds good. And just a second question, for the cobalt arsenic material, do you see two phase transitions in field or one?
There's an ordered state, and there's a number of different ordered phases in there. So we in the ordered state, but presumably you mean out of the ordered.
Yeah. There's some phase transition coming out of the ordered.
Not in our data. So we're starting high field experiments, right? That are kind of beyond. We're doing these in our lab, so we're restricted in terms of small fields. There can be possibly interesting stuff happening at larger field, but we didn't see anything in evidence in our data.
So for up to what field are you seeing the one transition?
Well, so this transition happens about 3.5 Tesla, and we measured up to 6.5 or 7 in that data that I showed you. Yeah.
Thanks.
So when you're doing your terahertz spectroscopy, you argued that you use the magnetic field to couple to the chains. Now, at least in principle, there's also an electric field coupling, yeah, because you have in an electric field, this angle of binding will change, and then you get kind of staggered J terms which couple to the electric fields.
Yeah.
Did you think about those? Could they be sizable?
Yeah. There's and these presumably depend upon the presence inversion center on the bond and those kinds of things. So these things have been discussed. I haven't spent a whole lot of time thinking about them because my interest was kind of more on the dynamics of the chain themselves. But there is a community of people in the terahertz world who are interested in the interaction, kind of light matter interaction directly. My guess is in this particular case that the interaction is purely magnetic dipole just from its intensity. So its magnetic dipole interaction is basically two factors of the fine structure constant smaller than electric dipole.
Yeah,
and
electric field is larger than magnetic field again.
What's that?
So the electric field is also more efficient than the magnetic.
Yeah, that's what I was saying. Is that the magnetic dipole is two factors of the fine structure constant smaller than electric dipole. So the electric dipole is generally much more efficient. If we have electric dipole absorption in some material for a sample this thick, we just won't get any light through, right? So it a thin film of something which has electric dipole needs to be tens of nanometers thick, and this is hundreds of microns.
At least in some chain components, we looked at the symmetry allowed to have this electric field coupling, and should be there and could be sizable. And let me say,
could be symmetry allowed, but I suspect it's not here because it would be far more intense.
Okay, so let me just add one more sentence. So if it's there, then one can also play games of creating a heat pump with that. Yeah? Namely, then when you put in polarized light, then there's a symmetry breaking that the kind of heat count to the right is different than heat count to the left, depending on the polarization of the light. And then you can, for example, prediction would be that that one side of your sample is warmer than the other side of the sample when you put in polarized light. Yeah? Due to the interplay of this electric and magnetic field coupling, that's some of the games you can play with these things.
Yeah. Okay. Let's talk about that. Yeah. I mean, everything that I've shown here is really the limit of linear response. So, kind of on purpose, the fields are small. So we're trying to induce nonlinear effects in these compounds, but those nonlinearities are small, and heating is a unromantic version of nonlinearity in this regard. So we're not in that limit here, but we could be in the future.
So I have a very naive follow-up on this one. So since I should visualize this as some kind of ESR experiment, can you give me a rough feeling of the size of the magnetic field that I should think of from your laser table pulp? So what's the magnetic field I should think of?
Okay, so first, just possibly unimportant comment. It's not a laser; it's a pulse. We use lasers to make the pulse, but sure. Just let's see. So the electric field is about 1 kilovolt per centimeter, and so that will correspond to about a Gauss.
A Gauss.
Yeah. So I think that's right. So 1 megavolt is 0.4 Tesla. So. And so this is 1,000 times less than that, or even maybe 10,000 times less than that.
Okay. And then one question to the data in the high field. That's probably just an experimental thing, but around 6 Tesla, it seems like on the lower gap, the intensity almost goes away and broadens. Is this just some experimental thing going on?
Let's go to
yeah, right. So around 6 Tesla, right?
So it's
the
just
green curve.
The low energies are, so I'm plotting out the kind of the low energy threshold of these features, and it's just passing below the low end of the spectrometer.
So the green line almost just vanishes. It gets broad.
The green line in the middle up here?
Yeah.
There's a bunch of details. We did these experiments in Estonia because they had the large magnetic fields. There's a bunch of technical issues with this kind of way of doing the experiment that you get standing waves. If you're referring to the multiple features in the spectrum, that's from this kind of technical issue. I don't know what you mean by it's disappearing. Maybe you can show me what you mean. Yeah. Thanks.
Okay. Yeah, thanks for beautiful talk. So as a big fan of Ising chain, I'm very happy to hear that. So perhaps I should resolve by myself, but so if you suppose you are at the critical point of the original transverse Ising chain, then introduce just a bond modulation like in SSH, then it opens up a gap, I suppose. But this critical behavior is the same as changing the transverse field? Is that?
So maybe you can just restate. I didn't quite.
So suppose you are at the Ising critical point,
Yeah.
the standard
Yeah.
transverse Ising chain at the critical point.
Yeah.
Then, so of course in experiment you cannot do that, but suppose I just introduce a bond modulation, then it opens a gap like in SSH.
Yeah.
And that quantum critical behavior is same as changing the transverse field from critical value.
Is that a question?
Yeah.
Yeah. Okay.
Maybe I should
so,
do the calculation by myself. But,
you know, as Koldea and Parameswaran said, that this system so the actual symmetry that's being broken there is not the Ising symmetry, but is a glide symmetry. And that's still in the Ising universality class. And so that's ultimately why we get this factors of 2, universal factors of 2. So I'm not sure if that answers your question or not, but if we had a staggered G tensor, that would be very different physics than what we have here.
Most of the update you wrote was away from that.
Yeah. That's right. Yeah. Yeah. But ultimately, when you get most close to the critical point, all of this non-universality, all these interesting features are not relevant, and you can pick up universal features, right? So that's a, kind of a nice addendum to this story, is that despite all of this other kind of stuff that's going on, this interesting complexity, you still see the universal features of the Ising universality class near the transition.
Okay, so let's thank Peter again. We have coffee break. We have coffee break now, and we restart at 11 o'clock.